These are the components of, I'm going to connect one sensor to one called access point or gateway or cluster head. Both of them are the TI experimenter boards or sensor modes, but the way we configure them or the software that we put on them defines their role in the network. So this is the gateway. It's connected through a USB cable to the PC here, and the USB cable will. There's a serial communication protocol emulated over the USB. We don't actually use USB. It's just a UART serial communication. And you know what UART stands for? Universal asynchronous
receiver
type. Okay. All right, and the sensor mode here should be connected to sensors. Now, the way we connect the sensors is, here are the sensors. We have two accelerometers. One is measuring the vertical component, and one is measuring the horizontal component. We place this. The civil engineering people would know how to, orient this or place it. Now we connect those sensors to what we call a signal conditioning board. Now this mode does not read directly or power this sensor. You have to go through a board or a signal conditioning board that powers the sensor and put the signal into the proper conditions that this mode can read, or the A to T converter in this mode can read. So the way to connect them, there are labels on these cables, the plus and minus. There are two set of pins here that are also labeled plus and minus. So you connect the right ones, the plus to the one labeled as plus, and the negative one to the one labeled with the minus sign. All right, do the same for the other sensor here. Okay. And then we connect this signal conditioning board, both of them, to the sensor mode here. We kind of designed the cable that connects 3 signal conditioning boards, but we're going to use 2 of these now because we will have only 2 sensors. So there's only one way to connect this, and that's the right way. Okay. Now this cable has 3 wires. One is we call it power line, one we call signal line, and one is ground. The red wire is power, the white one is signal, and the black one is the ground. And on the board here there are pins and port and pin numbers. So if you read the labels on these pins here, you have something like 5.1. This means that this is port number 5, pin number 1. Then 7.4, 7.6. If you go to the manual, and you could see that some of these pins are connected to the input channels in the ADC module on this microcontroller. Okay, so the way we connect them, we're going to connect. So one of the pins is power, and by power I mean this is a signal that turns this on and off. So there is an electromechanical switch here that turns this signal conditioning board on, and hence turns the sensor on, and that is controlled by the sensor mode, and that control signal comes through the power line. Now once you turn that on, the signal conditioning board will start getting the signal from the sensor and feed it back into the signal wire here. That goes into the in the input channel of the ADC where we sample the signal. Okay. Now the way we configured these, you could see the pin configuration and in the code. We will get to that now after we finish, describing the components here, which we're pretty much done with it. Now, just one more piece that has nothing to do with the setup is this small piece here. This is packet sniffer. That it has the same, almost the same RF chip that is here. It's an IEEE 802.14.4 chip that reads any packet on the air and sends this to a packet sniffer software here that we're going to use to debug the network and see how the packets are being transmitted. Okay, so that concludes the hardware part of the setup. Now going to the software, this is the main project for any node in this network. You could configure this in 3 different ways. You could configure it as for an access point, and that's the cluster head, or for an end device, and that's the sensor mode that's connected directly to the sensors, or as a range extender. Because we're doing a single hop network, we don't have range extenders in our network. We only have access point and end devices. So right now I'm gonna program the access point, so I select this as the configuration here, and I wait for the configuration to change. The name here is going to change from end device to access point. And while we're waiting on that, I'm going to connect the JTAG here to the gateway or to the access point. And if you look at the folders here under this project, there are the includes folder. It's a folder called includes all the library files that you need. I mean, there are different libraries here. We have the board support layer. You have the USB. You have something. The file that you include at the beginning of each file, the one that defines this version of the microcontroller is included in this one. Drivers, there is the RF interface, they call it the minimal RF interface layer is defined here. Network layer from Simplicity is also, all the files are included under those subfolders in the includes. And here you have projects. So we have the different configurations that you need. If you are doing an access point, here are your applications and components that you need for that. And if you are doing an end device, it will be here. And if you go under application and expand everything, you'll see here, if you expand all the way to the files, you'd see some C files here where the main functions for each device is defined. So now if you expand all of them, see there's a cross on each of these files. By selecting different configurations, this will include or exclude some of these files. So you have all the files, but not all of them are used in compilation or in creating the binary that goes on the flash memory on this CPU. Depending on the configuration. And here I'm configuring this as an access point, so it's only including this file. All these, if you see the little signs, as that means that this file is not included in compilation. And there are 2 versions of for each file. For the access point, there's a main function where you include an auto ACK. You know what an ACK message is? It's an acknowledgement. When you send out a message, you receive it back. You could add this or exclude it, depending on what configuration you want. So if we go to this file here, the one that does not have ACK, for example, let's see this one here. And look in the file here, you see all these files that were in the includes are included here. I'm not going to go in the details of the code, but you would I mean, each of these statements has a documentation or a comment next to it that describes what it does and what function or routine does it invoke. Important things are to initialize your board. So Simplicity has to understand what board or RF is dealing with. So you initialize this with the BSB init, and then you initialize the USB for the this communication here. And I think you've done this in lab 3 or 2, the USB. It's pretty much the same code. It's just, you know, customized for this application here. And then I don't know how far you went into the Simplicity code. Then here starts the Simplicity routines or functions. Here the gateway will start listening for any node that wants to connect, and it will, you know, it will go into an infinite loop waiting on something to or on one node to send a join request. Once that happens, it goes into this if statement and does, you know, something that you define. It's up to you to define. In this case, I define commands that I send. You know, once this device sends a join message and the join is successful, it returns a Simplicity success. You go in, the gateway defines this command SS, which means start sampling, and send it out, put that in a message, and send it out to the mode to start sampling. Okay, and here there's the sjoin semaphore. It's a variable that keeps the number of peers. You could, in the configuration file, you could put a limit on the number of nodes that can connect or join a single access point. So this variable here keeps the number of them. So I mean, you set this to the maximum and then decrement it every time you one of the sensor nodes joins the gateway. Okay, so let's compile this. First, you have to, you know, build it. Build and compile. Feel free to ask any questions while we're waiting on this, if you have anything. I'm going to run this in the background. But just one thing before we go, I should have talked about. Here is the configuration file for each, the end device and the access point. They have a configuration file where you define different parameters that you could change depending on your network or what you want your network to do. There are queues for the number of frames that you can queue. You could define the size of these, but most important thing is the configuration file defines the role of the device and it defines its address. So you want to make sure that your no two devices have the same address, because one of them will end up, you know, being knocked out if they exist in the network. So this, I mean, as you can see here from the define, this defines an end device. If you want to see the configuration for the access point, you go under this folder here and okay, I'm gonna find this file here. Yeah. Under applications, there's a folder called configuration, and if you open this, you see the configuration for each device role. The one that you need to keep changing is the end device, because you will have multiple end devices, but you would have only one access point if you're implementing just one cluster of nodes. So as you can see, there's more configuration parameters in the access point. You have the number of concurrent connections defined to be 8. The size of the queue is larger because this one is receiving more frames than an end device. In this case, we have 6 frames or 6 packets. The address here is, if you compare the two, I tend to, the address is 4 bytes. It's 1, 2, 3, 4. Each of them, one of these bytes is written in hexadecimal. I tend to leave the way they are written in the device is in the reverse order. So this is the lowermost byte, this is the second lowermost byte, and this is the highest or the most significant byte here in the address. So I keep the two most significant bytes the same, and I call this the network ID. So everyone in this, or the cluster ID, everyone in this cluster would have the same upper 2 bytes, and you could change the lower 2 just for different devices. So I mean, and even in this case, even the 3 upper bytes are the same because we have a very small number of nodes. So I only change the lower byte. In this case, the access point is hexadecimal 11, and the end device is 44. Okay. Okay. So going back here, we have warnings, but you could ignore these. And then we have a successful compilation, no errors. So we burn this on the access point. Okay.
I think
update. I'm trying to find a shorter way, but I'll wait for it to update. Okay, so we have a successful compilation on the gateway. Because we're communicating with the PC here, I'm gonna run the MATLAB code to talk to this, but I have to verify the port number first. So if you go to my computer, our device manager here, properties. Let's see the ports here. So it is, there are 2 TI or MSP ports. One that's the JTAG, and one is this USB connection. So the serial port is COM4, so I just want to make sure that I'm reading the right port number. This is MATLAB here, and I think I have the right. So the file is get data, it's COM4. I define the baud rate to be 115.2K. Define a file name to write the data to. And all what I need is to run this actually. Check folder. And now it is running. Okay. All right. So now the up to this point, we have the access point connected to the MATLAB, and it's waiting for some sensors to join. Okay. I believe this sensor already have the end device code in it, but I'm gonna do it anyway, do that again just to show you how to get the pin numbers for each channel here. I'm gonna stop the debugging here, go to the, again, we're done with the access point. We switch the configuration back to end device. Give it some time to do that. And while it's doing that, I'm just going to run the sniffer. So the sniffer, well, it's done. We'll come back to this later. So now the project is configured to the end device configuration. As you can see, now the main function here, or the main file for it says excluded from build. This is the only device or the only file with the main function that is included in the build. So if you double click on this, we'll open the file, and here we have pretty much the same initial configuration, but you would see a different code at the end. But some of the things that here that I have added are very specific to the vibration data acquisition application. I defined 3 buffers, each one of size 2.4K bytes, actually 2.4K words. This data type is an unsigned integer of 16-bit. So we have 3 buffers each for one of the channels, X, Y, and Z. But in this case, we only have 2, so you need to modify that. It's not gonna, generate an error if you don't have that. It will just fill it with zeros. But if you're only gonna use 2 sensors, it's better to, cancel one of those buffers because, to save memory for other things. Set up the DMA. Then initialize and initialize the real-time clock, and that's for synchronization. I did the same on the gateway, and here's the code where it links to the gateway or to the access point, and that all part of simplicity. We're gonna go into details, and here's how it samples the data. Takes the right size from each. I mean, it took a lot of time to get this right because the DMA is reading data from the ADC, put that in memory, then the CPU comes take a certain size from that buffer, put it in the packet and send it to the RF. So it's not the CPU that's doing everything. So you want to make sure that you are keeping everything in sync, that the DMA and the CPU are not overwriting or reading, the CPU not reading garbage, or the DMA is not writing on data that has not been read by the CPU. And trying to find the pin numbers for the ADC. Yeah, here. Okay, so the ones marked, so I mean, from the variable name you would see which channel is what. I mean, here we have accelerometer X pin and accelerometer Y pin and Z pin. These are for data. Okay, so the ones that if you look at the pins here, there's one ground pin, so that all the ground wires that coming from here. Let me go back again and talk about these wires. We have 3 wires coming from each signal conditioning board. We have a signal, we have a power line or a control line that controls the switch here. That's probably a better name for it. And we have a ground. On this side, we have input, or we have pins that are configured as input pins to get the signal. We have output pins to control the switch on the signal conditioning board, and we have a ground pin. So we have only one ground pin, so we need to connect all the grounds together, and that's what we did here. This is why I suggested that you find a better hardware interface for this, just to make things less chaotic. So we connected the grounds together here, and we connect this. If you zoom in the camera, this is the ground pin here. We connect the yellow one and the ground. And now what we need to know is which one is configured as power and which is configured as signal among these pins, and that's something you could find in the code here. I think I defined that in a header file. Let me find that header file. It's in axela.h. It's probably already open here. Okay, so here, if you go to axela.h, you could see the how the pins are configured. So 7.4 and 3 points. So the way I did it, it's the pin numbers. So I used port 3 as power and port 7 as signal, and then the pins 4, 5, 6 and 4, 5, 6 from each port. So 7.4 is signal for channel X, 3.4 is power for X, 7.5 is signal for Y, and 3.5 is power for Y. So 4 is X, 5 is Y, and 6 is Z. And port 7 is for data, port 3 is for control of power. Okay? So let's connect X and Y here. So the white, let's say this is X, you know, the vertical component. We take the signal wire here, the white one, and connect it to 7.4. And here's 7.4. The second pin, and then we connect the power to 3.4. And same thing with Y here, so we connect the signal to 7.5. and the power to 3.5. I mean, it's difficult to move around with these, but once they are in and they're, I'm going to use this wire here. We definitely need something easier than this to...
Yeah, they are looking for that now, so
Oh.
we should have something within a week.
Okay, so we have them connected. We have the ground, we have signal, everything. So we just need to. It doesn't matter because we only have one sensor. So the address, it's just we want to make sure that it's different from the access point that's in that configuration file, and it is different. So we go to the main function here and compile or build a project. Alright, so we're ready. We need to burn this to the device.
You have to disconnect it and reconnect it again.
Sometimes I just do this. Just provide more current through, because this is this is a bug that TI talked about. It's a problem with the current that does not provide enough current. It's ready here now. I'm just gonna connect this back to the gateway. Before I start anything, I just want to turn on the sniffer so we can see packets, see the direction. So you plug the 2531 module here in the USB, And then when you turn on, you need to download this. This is a free software that you download from TI.
Okay.
And there are a bunch of protocols that you use. You always capture a packet, but then the way you interpret the field is different from one protocol to another. So you could either choose, 802.15.4 Zigbee or another Zigbee out of 4CE or simplicity. So our protocol is simplicity, and you hit the start here, and then you start listening to the packets here. One thing is you have to make sure is that you are on the same channel as your second, because Zigbee or the 802.15.4 has 15 channels here. You need to make sure that you are on the right one. I think they're configured to operate on channel 16, which is 1A in hexadecimal. So, and you hit the on, and now the way we're gonna do it is we're gonna go to MATLAB and turn this on. And let me try and turn this. See, we're receiving something here, some packets. Actually, what you're seeing here are something that I didn't talk about, which is the synchronization packets. If you look at the destination address here, it's FFF all ones. This is a broadcast message coming from, wait a minute, it's coming from 4455AA. You remember which address was that? It's the end device. Yeah, so that means that there is something wrong with the configuration. Let me take this back here. Means this is not on. Actually, this is not the synchronization. Sorry, this is the join message. Yeah, I mean you could see the join now. So this guy is trying to join this, but for some reason this is not listening. Okay, it's coming from here, but this guy is not listening. Let's see what's going on here. I think maybe it's not. So it's going to keep sending those until it receives some feedback for the connection. Okay, so again, let's go back and change this to access point. Right, we were not, okay, now we should get something now. Okay, I know what's wrong. Okay, yeah, we're getting packets here. Let me stop this. Okay, so what happened is I just need to change the switch because I was powering through USB, not the FET, and the switch wasn't the FET. So I turned it on, and now this is the simplicity protocol. This guy keeps sending join, and then the access point received that and send out a link to you see, once it hits something, it sends out a link, and this is the linked token that was sent from let's see, let's go back. Okay, so beginning from this point, there was a broadcast message from this guy, from this source address 44 to any listening gateway. Then they negotiated the port which they wanted to connect on, and they chose port 3F. So this message was from this guy out as a broadcast that I'm listening at this port if you want to connect to me. and then the join message was sent for this port again, and then this responded with the link message. I mean, you could trace the messages, but this is the handshake that goes on before any connection starts. And then what happens is that this access point sends out a start sampling command, and then you start getting the data. And the way data is being sent is, if you look at the pattern, you would see I think 9 packets and then 1 short packet. And then, I mean, as you go, and it will always be 9 and then 1, 9 and then 1. And those are the little one here is the destination is all ones, and the source address is the 1 1, and that's the access point. This is actually the synchronization that's being sent every 1 second, okay? And the value that is in the payload is the counter that is counting inside the access point.
Come on. Keep going.
So, and you know, because we are sampling at 100 samples per second, and we have 3 channels, you know, remember, although we're connecting to a sensor now, but this mode, sensor mode thinks it's a 3 sensors, because that's the way it was configured. So we get data from 3 packets from each channel every 1 second. Each packet would have 33 data samples. So 33 times 3, that's 100, 101 per second being sent in 3 packets, and we have 3 channels, so we have 9 packets every second, okay, coming from one node. In the case in that experiment that we had more packets because we had more sensors, obviously. If we run this and see, I mean, there's, you know, now running, still getting some data here. Now, the way we, if you look at the payload here, it's, you'd see similar data at the beginning, and that's the way we formatted this packet. 0C, I think, was the application ID. We could, you know, I forgot the exact field names, but we can send you that. First byte I defined application, and then there was 1 byte that identifies the source where it comes from. Those are 4 bytes, and then there is a timestamp, and then the data. I mean, if you look at the whole packet, it's really long packet. And that's the port that I used for data. I just picked that port number 20. And you could see more information about, you know, the link quality, the RSSI, which is the received signal strength indicator. If you move this thing out, you would see lower values for the RSSI. And that's just because it's next to it. You could, you know, it's minus 61, minus 51 dBs. And the last part here is the forward checksum, or it's a checksum that makes sure that the you know, or you know, preserves the integrity of the data. Just make sure that your data is right. Okay. Now MATLAB here is not showing anything here because it's writing everything on a file. So and if I just close this one here, I believe the data is. Let me just double check the name of the file. So it was Axelo data test 0. I think it's this one here. Yep. We have to restart MATLAB. And once you get that exception in order for
Did
the...
we close the channel before we started recording them?
Yeah.
Close that completely.
There's no way to kill that thread. But anyway, that's the. Let me show you one of the files that we had, and the way I store the data. Here, we remember the Georgia game. I mean, this is pretty much the way the packets are stored. Usually at the beginning, because the sensor takes some time to settle, you will get zeros or all ones. And as you scroll down, maybe not this one, wait. Actually, this one is a split data. Let's take something that is not split. Okay, yeah, this is from different. See, at the beginning, all the channels would be like all ones because they're not. The sensors had not settled. They take like 45 seconds to, and then you get the data. And I think the way I start, if you look in the code, you would know those fields from the code of the access point. Let me go to that and show you how to figure this out. This is the device. Here's some of these. I mean, how to. There's the length of the message, the source address, the received RSSI, the link quality, the transaction ID. They're all being written here. And then when you process the message, it's a process message that writes that to the USB. And I think it's right here. Yeah. So process message takes these parameters here. So the first thing you send over the USB is the RSSI. So this is the received signal strength. And then the transaction ID, then the address, the source address, which is 4 bytes. And then the transaction ID, then the length of the message. And then if the length is greater than 1, you have data. Then you write the whole message. I think all of you know this function, right? USB send string.
Mm-hmm.
That's from. So you give it an array of characters and the length of that. So that's the way you know how many data you have. You read the packet, you read the length field, you know how many bytes you have in the payload, and you use this function. You give it a pointer to the message with how many bytes to read from that. So, and that's being sent through USB. So the fields here, the first one is the RSSI. Then you have this is the source address or the address of the source mode, and from this data is from that experiment that I did last fall. If you see, you have 3 different sources. The addresses have the same 3 bytes here, but the lowest significant byte is different. You have 3, 4, 51, and 68. Okay. And again, this is, I mean, if you look at the configuration, the addresses are AA. This is hexadecimal, but here it's decimal, so AA translates to 170, and 55 translates to 85 in decimal. And then you have the transaction ID. The transaction ID is important because the end device is programmed to increment that for each packet. So each packet, this is like a 1 byte sequence number for each packet. So if you look at all these 3 packets here from this device, 34, and you look at the transaction ID, you see it's 120, 121, and then 122. And then you get 3 packets from a different device, another 3, and you come here, you see it continues on 123, 124, 125. So when you take the data that came from this device out of this file, you would see that the sequence number is, or the transaction ID is incrementing by 1 for each packet, and when it reaches 255, it goes back to, because it's just 1 byte that's used for that. So it's good to know the order of the packets, because the order of the packet is important, because you have time domain data being collected from here, and you know how to, which packet comes when, and you have to know the right order of them. And then we have another next to that is the length, and as you can see, I mean, the length is fixed for all packets. It's 78, but that 78 is only the payload. It's not including this. And then I believe the 4 bytes, I mean, the message itself, the first 4 bytes of the message are the timestamp. The timestamp, and then you get the vibration data comes after that, okay? And again, this is a 32-bit that was broken into 4 bytes. You have to do some alignment and, bitwise shift to get the right number out of this. Okay, and here comes the data. And as you can see, because this is a 12-bit number represented by 2 bytes, it's always one of the bytes have a small value and the other one has a big value. And actually this is the lower byte and this is the upper byte. Because it's, this only 4 bits are used here and the whole 8 bits are being used here. You get this point? Yeah. And that's pretty much it. Now, what you want to do is to take this MATLAB code here and try to implement it on the cluster head. That's should be fairly simple. Okay. There's one thing that you will see frequently in the simplicity code, and that's frequency agility. There is something in the configuration we could enable or disable this. And frequency agility means that if the channel that you are operating on has a very bad RSSI, I think it samples probably 3 or 4 values of RSSI. If it goes below a certain threshold, then you switch to a different channel and use a different channel. Okay. But in this case, as you can see from the packet sniffer here, I'm using channel number 26, and that's a number. I mean, the actual number of the channels are 15, but they start at 11 and they end at 26. And usually those 2 channels, we use them because they do not overlap with Wi-Fi. 802.15.4 operates in the 2.45 gigahertz, and that's the frequency where Wi-Fi operates as well. So if you look at the channels, the Wi-Fi channels and the Zigbee channels, you'll see that those 2 do not overlap with the Wi-Fi channel. So if you have a Wi-Fi access point near your sensor mode, you know that it's not going to kill it. or kill the signal. There's also channels, I think 15 and 16. Now, we don't use all of the Wi-Fi channels, and we usually use channel 1, 6, and 11 from Wi-Fi because they also do not overlap. So there are in between, I think, channel 6 and 11, channel 5 and 16 from Zigbee. You could use those as well. So now, if you want to do frequency agility, you could define what channels to switch from. So you don't, jump to a channel that overlaps with Wi-Fi. So you could choose 15, 16, 25, and 26. Those are the 4 channels for the frequency agility to keep hopping from one to another one. Okay, and I think that's it. That's all what you need to get started. Of course, you have to dig in the code to understand what what it does and what you need to modify to change the application. All right.
Board is on.
Yeah. There is a light. Yeah, you can see this light on. Yeah, sorry, I didn't mention that. I mean, we should have seen that when you turn this on and the connection goes, you could know from this LED here. It's on. This means that but some of them have a bad LED. So let me see if this one. Yeah, see this one here. The LED is taken off. Actually, somebody took off because it was bad. Yeah, this is number 9. See. Only LED. This says that the LED does not work, so everything works except the LED. But most of them, if they don't have this label on them, this means that the LED is working, and that way you know that your channels are on and that the power is off. And